So now let's talk about real processes. If I want to know what's going on with an irreversible process, let's go back and start with the Clausius inequality. So, I'm not going to go through all of the details. I'm just going to kind of outline the plan. We basically want to consider two different cycles. Both of them are made up of two processes. I'm going to go from A to B reversibly, but I'm going to go from B back to A two different ways. In one cycle, I'm going to do it reversibly, and in the other, I'm going to do it irreversibly. Okay? So if I do that, then I can say that the net dq over t is going to be positive, or it's going to be negative or 0 for my two different cases, and I end up with that delta s is going to be positive or equal to this for reversible or irreversible. So whenever I get delta s equals dq over t, it's a reversible process. For irreversible processes, delta s will be greater than dq over t. Now, this is how you would calculate delta s, right? But it's got an inequality. I think engineers find that to be disturbing. So what we do is we get rid of the inequality by adding something positive to bring them up to equal. And the amount of that something positive will vary depending on how irreversible the process is. Okay, so I'm going to add entropy generated. Now, entropy is always going to be generated, meaning it will always be a positive quantity, unless, of course, the process was reversible, then it will be 0. But entropy generated can never be negative. But now I've created an equation out of that inequality. So if I look at this in real processes, I can relate the heat transfer of the irreversible process to a reversible process using those TDS definitions. And so heat transfer for real irreversible processes will always be less than the reversible heat transfer. Okay? If you use that with the first law, then I get that the work of an irreversible process, this is the work of a reversible process, minus something negative. The work of an irreversible process will always be less than the work of a reversible process. Okay? So there are some key concepts that we can draw out of this. First, entropy increases by transfer of heat to the system or by irreversibilities. Okay? So there's two ways I can have entropy transfer, okay? But it can only decrease by heat transfer out of the system. Otherwise, entropy will increase unless I have heat transfer out of the system. Second, irreversible work is always less than reversible work. So if I am doing an expansion process that will produce work, I will get less work out. On the other hand, compression processes where I have to put work into the system, it's negative, and so if I'm less than a negative quantity, it means I'm putting in more work to do a compression process. Then finally, for real irreversible processes, work isn't the integral of PDV. And for real irreversible processes, heat transfer is not the integral of TDS. So that means that the area under the PV curve gives reversible work, but not actual work. And the area under a TS curve gives reversible heat transfer, but not actual heat transfer. Now there's one last little topic in here, and it's the principle of the increase of entropy. And we've been looking at just a system and only concerning ourselves with the system. But it is actually helpful to go and look at what happens overall, because our systems are surrounded by our environment. We care about what's happening there also. And so one of the things that I can do is I can look at the entropy change for the system, comparing it to heat transfer divided by temperature, but then also look at the surroundings, which are at a different temperature, T0, or the ambient temperature, the temperature of the surroundings. So what's going to happen to the net entropy change? Okay, so it's going to be what happens to the system and what happens to the surroundings. the amount of heat transfer will be the same. It goes out of one into the other, so the directions will be different, but the amount of dq will be the same. So dq times 1 over T minus 1 over T naught is the net entropy change. Now I've either got two possibilities. I have case 1 where heat is going into the system from the environment, meaning T naught is larger, or I have the case where the T of the surroundings is smaller, meaning that the heat is going from the system into the surroundings. And either way I do this, when you play with the numbers and look at the signs, I end up with it. The net entropy change is positive. So always the entropy change total is larger. Now a lot of times people will use this to relate entropy to chaos, okay, indicating that the world is becoming more and more disordered. And it is indeed a very helpful way of examining and considering this in terms of just getting a basic understanding of what entropy means. Okay? It's not going to exactly be true, but with any analogy, it's not going to be exactly true. So now think about this. Imagine that your room is a mess and your mom is coming to visit you. So you very hurriedly go cleaning your room. By the end, you should be feeling that, oh my goodness, I have put so much effort into putting that back into position. Everything is straight and orderly now, but me, I'm a wreck. My system has changed its entropy in order to change the entropy of the room, okay, to change that order and chaos. So again, it's not a perfect analogy, but we understand that overall, that change had to come from somewhere. If one of them decreases, the other one has to increase, okay? Overall, it will be equal to 0 for reversible, positive for any real system. Now, one last little thing here is that if I have an isolated system, in an isolated system, there's no communications with the surroundings, in which case I only have the system. That means that isolated systems can only have positive entropy changes. In section 612 of your book, just as a suggestion, you might want to take a look at that. We look at that as a rate equation. It's going to help us get started in the next chapter. And then they have some general comments about entropy and chaos. It's actually a very interesting read. I suggest that you read this one on your own.